So let's continue practicing solving logarithmic equations. Remember, solve just means to get the variable by itself. Here's our variable. It is not by itself because of log base 36, but something you need to think about. When you have log base 36 of x, they make up an entire unit. In other words, we can't just simply try to write something like log 36 and think it's going to cancel out, because that's not what can happen here. This is the base and this is the component, and they're all a unit together. So we can't simply eliminate the log base 36 by dividing by it. That doesn't work. Instead, we have to think about it of, well, how else could I rewrite this function? I could take the base, raise it to this power, and write it in exponential form. So let's do that first. 36 to the 3/2 equals x. From this point, we can just use our calculator and type that in and see what 36 to the 3/2 powers equal. Typing it on the calculator, we get 36 to the 3/2 power, which is 216. So x is 216. Now to check it, we would just have to take the log of 216 over the log of 36, which is our change of base formula. Let's type that on the calculator. Log 216 divided by the log of 36. Sure enough, it's 3/2, so we know that we're correct. This next one, when we try to solve it, we notice that they both have a log on each side, just one logarithm. Both logarithms have a base of 2, and then they both have some component next to them. Since they both have the same base, we can instantly set these pieces equal to one another and just eliminate that log on each side. We're not actually eliminating it, but we are saying that since they have the same base, what they are set equal to must also, or their components must be set equal to one another. That's what I'm trying to say. All right, so when we're solving a quadratic equation now, we need to get it equal to 0 by subtracting 3x on both sides. This is pretty simple to solve by factoring, or we could use the quadratic formula. Factoring seems pretty simple. What multiplies to -4 and combines to -3? This means x equals 4 or x equals -1. Now remember, we need to check these. We need to put both of these solutions back through. So let's check x equals 4 to make sure we didn't pick up an extraneous solution along the way. The log base 2 of 4 squared, 16 minus 4 is 12. Does that equal the log base 2 of 12? Remember, we have to sub it back into the original equation. Sure enough, when we do this, those are the same thing. If we plugged in the change of base formula of log of 12 divided by the log of 2, it would be the same on either side. Let's try the other one. We have log base 2, -1 squared is 1, minus 4 is -3. Log base 2 of -3. Now granted, they are the same, but what happens when we try to type that on the calculator? The log of -3 divided by the log of 2. We get an error, non-real answers. And if we go to that error, it says you cannot have a negative right here. And we know that because if we just isolate this piece, log base 2 of negative 3 equals some number, I'll call it y. If I try to write that in exponential form, 2 to raise to what power gives me a negative number? Nothing. That's impossible. So when you substitute it back in and you have a negative quantity right here, you know you've picked up an extraneous solution and we have to throw it out. Exponential growth and decay. Here are a couple other formulas that we can use to model exponential growth or exponential decay. It's very similar to models we've been using, except in this case they're using K to represent the rate of continuous growth instead of R for a rate. And a lot of these formulas make a little bit more sense when we actually apply them to a real-world problem. The half-life of a radioactive substance is the time it takes for the half of the atoms of the substance to disintegrate. The half-life of carbon-14 is 5730 years. Determine the value of K in the equation of decay for carbon-14. Since we're talking about disintegration, we're talking about something decaying. So we want to grab the decay formula. F of T equals A e to the negative k t. Notice A is the initial value. We don't know how much of the substance we're starting with, but we know that the half-life means there will be half of that in the end. So we don't know how much we're starting with, but we know we will end with half of it. So we put half A on this side. Then we have e to the negative k, and we also know time, 5,730. They want us to determine the value of k. They're asking us to literally figure out what this variable is. Determine the value of k. Sometimes you need to highlight that in your word problem so you know what you're solving for. We have 3 different letters in this problem. We don't have 3 variables because remember E is representing a number. But we do have multiple variables, so we need to be sure which one we are solving for. We are trying to get k by itself, so let's first start by dividing both sides by a. When I do that, I now have 1/2 equals e to the negative k times 5,730. In fact, I could actually do a better job writing that because we usually put the number first and then the variable. K times 5730 is 5730k. All right, now I am still trying to get k by itself. I'm solving for k. I can't get k by itself when it's taking on the role of an exponent. So I need to take the natural log of both sides so that this exponent can jump over the log and become a coefficient. So on the left, we still have the natural log of 1/2. On the right, my coefficient is now 5730, which used to be the exponent. My exponent has become the coefficient. Remember, the natural log of e is just 1, so it's gone. And I'm still trying to solve for k. I'm getting really close. All that's left is this coefficient dividing by 5730. Excuse me, negative 5730, of course. Let's type this on our calculator. The natural log of 1/2, just going to use 0.5, divided by negative 5730. Now this is a very small number actually, because it's times 10 to the negative 4th. So 1.2097 times 10 to the negative 4th. Move this 1, 2, 3, 4. That would be my answer. A reasonable answer would be to say that the rate is 0.00012. It's probably enough decimal places to round to. All right, now they're telling us that the half-life is 24,000 years for plutonium-239. What would be the value of K? Well, let's start it off again. The half-life means half of what we start with equals what we start with times e to the negative k t, where t is 24,000 years. Dividing both sides by a leaves me with 1/2 equals e to the negative 24,000 k. I take the natural log of both sides. My exponent can now become my coefficient in front of the logarithm. Oh, you know what I just realized? I put an extra half in there that I did not need. My eyes must have been looking at the left side. It's just the natural log of e, not 1/2 e. I apologize for any confusion. Divided by negative 24,000. K is approximately, let's check it on our calculator, the natural log of 1/2 divided by negative 24,000. It's an even smaller number, 0.000 1, 2, 3, 4, 5, 8, 9. There we go. A very small number. A very, very, very small rate. Equation y equals ae to the kt is identical to the continuously compounded interest formula that we've been using, the APERT formula, where a is the amount at time t, what you end with, y is the population at time t that you end with, p is the initial amount in this formula, a is the initial population. I know that's confusing because in the compounding, capital A is the amount you end with, but in the population growth model over here, little a is our initial population. So that can be confusing. In continuous compounding, R stands for rate, and in population growth, K stands for the continuous rate of growth. But knowing that there are similarities between these two formulas does help us to manage them. So here we can't really use continuous compounding per se because we're not talking about money, we're talking about people, population. We want to figure out the value of K with this information about Georgia. In 2015, the population was 10.2 million people. In 2010, it was 9.7. So we are growing. We started with 9.7 million, but we end with 10.2 million people. So we need to multiply this by e to the kt. How many years have passed in between here? Well, that answer is 5 years. Now I must solve for k. That is our variable we're trying to solve for. I'm going to divide by 9.7 on both sides. Of course, the calculator will help us with this process. 10.2 divided by 9.7. Now, we want to try to keep from rounding until the very end. So it's better to take a moment to write out all of these numbers to show your work rather than to round. And now we have e to the 5k. Remember, we want to get k out of the exponent, so we need to take the natural log of both sides. In fact, when I do that, my 5k come down and become the coefficient of the natural log of e, which is simply 1. Now I have the natural log 1.051546392. All I have left is to divide by 5. Now, when I type this on the calculator, even if I type all 9 decimal places, I'm still actually rounding. So it would be better for me to say the natural log of my last answer, and I'm going to press second minus to get the answer to pop into here, and then divide by 5. That will keep my answer just a little bit more precise. 0.01005. Now let me show you what happens if I were to have rounded that. If I take the natural log of 1.05, let's say I rounded to 1.05, and then I divided that answer by 5. Do you see how I get a different number? Granted, to the nearest hundredth, they would both round to 0.01, but there is a rounding error that you would pick up if you don't try to keep as many decimal places as possible. The final question they're asking us is, when will the population reach 12 million people? To solve this, let's start with our formula again. We want to end with 12 million people. We were starting with 9.7 million people. E, we know what k equals now, 0.01005. And we don't know how long that's going to take. That's what we're trying to figure out, when. So let's solve. Let's divide by 9.7. Divided by 9.7 gives me 1.237113402, and that equals e to the 0.01005t. Taking the natural log of both sides allows for that exponent to become the coefficient. That just equals 1. I have to divide by the remaining coefficient. And again, on the calculator, I'm typing the natural log of my answer so I don't have to retype those decimals. And then I'm going to divide by 0.01005. And I get that t is approximately 21.17 years. But that's years since, what year did we start? This was in 2010. So if I add 21.17 years, that's going to be approximately the year 2031. That's when Georgia's population would finally reach 12 million people.